Okay, so before we get started today, a couple of things. I have edited all of the videos up to this point, and they are currently in the process of uploading to my YouTube channel. So shortly after class, I will put all the links on our Moodle page for you guys to access them. I have not yet written any of your homework assignments. My goal is to get 2 of them written this afternoon after I wrap up meetings and all of that kind of stuff and uploaded to you guys. I'm going to have to, be careful but also fair about what the due dates are. I would like to get one of them turned in prior to us heading out for break, but realistically, to give you guys enough time to do it and all that kind of stuff, that may be a little quicker turnaround than you're comfortable with. So we'll talk about that once I get the assignment uploaded and you can see what it is and see if you think effectively getting it in by Tuesday is too unreasonable or not. I'm willing to negotiate on that effectively. I'm not trying to give you guys a bunch of work over the break. It's supposed to be a holiday, so all that kind of stuff. All right, so today we are going to talk a bit about accelerometers. So this is the first classical MEMS device that we are going to look at. And we are going to use the accelerometer to introduce multiple different types of sensing that occur at the MEMS scale. So the accelerometer is probably the highest selling MEMS device by far. The reason why I say that is because the development of the MEMS accelerometer is really the thing that kicked off the commercial MEMS industry. We talked on the first or second class meeting about the 80XL series of accelerometers that were developed by Analog Designs in the, I want to say it was the early 1990s. Those were the accelerometers that were used in the automotive industry, and they are the reason why our cars have airbags and stuff now. It wasn't until the MEMS accelerometer was developed that we could reliably deploy airbags. So every vehicle that's on the road today that has been made in the last 20 so years contains at least one MEMS accelerometer, probably several, one for each airbag in the system. Then we have all of our cell phones, which usually have a couple of accelerometers in every single one of those. All of our laptops and stuff like that also, or at least higher end laptops, have accelerometers for fall detection, so that they can, if it has a magnetic media storage, it can move the read head away from striking the actual disk if your computer falls, so that you don't destroy your hard drive due to the internal mechanisms in it. Okay, so accelerometers are literally all around us. Okay. All right, so what we are going to look at is a simple classical accelerometer. Here I'm going to draw a little diagram that's going to try to relate everything here. So this external bit here is our frame, okay? And in our accelerometer, our frame might have some displacement XF. Internal to the accelerometer is some proof mass M, which may have some displacement, which I'm going to call X sub M, and a spring having spring constant K connects our inertial mass to our frame. And then there may also be some sort of mechanical damping present, characterized by the damping coefficient gamma, that effectively tries to in some way influence the displacement, the relative displacement of the mass with respect to the frame. So it's there to arguably prevent ringing and things like that. Okay. So just so that we're clear, M represents the mass of our proof mass. K here represents our spring, specifically our spring constant. And gamma here represents our mechanical damping coefficient. Alrighty, so effectively due to the inertia of the mass, if the frame moves, it's going to take some time for the mass to move. So there is a slight lag or signal lag that causes the movement of the mass to lag behind movement of the frame. We wanted to describe our system, we could develop an equation. So let's say that our equation here is mass is going to be multiplied by the second derivative of the mass displacement with respect to time, otherwise known as the acceleration. So we have a force, plus gamma times the derivative of the difference in displacement between our proof mass and our frame with respect to time. And then we're going to have Hooke's law. K times the difference in the displacement of our mass and our frame, because that tells us effectively how far our spring has extended. And this will be equal to Fe, the external force experienced by the system. Okay, so just to write these things down, Xm is the mass displacement. Xf is the frame displacement. And Fe is the external force acting on the mass, really acting on the system. Acting on the mass. Okay. So what I'm going to do now is I'm simply going to subtract the acceleration of the frame from both sides of the expression. Okay. So if I do that, what I get is the mass times the second derivative of Xm minus Xf over, or with respect to time, plus gamma Xm minus Xf with respect to time, plus K Xm minus Xf is equal to our external forces minus M and the second derivative of Xf with respect to time. Okay, so effectively what I've done here, my right hand side is simply the sum of the external forces on the system, or really the external forces and the inertial forces acting on the mass, because we're taking into account the movement of the frame as well as some external force. And on the left hand side, now everything is expressed in terms of that difference Xm minus Xf. So we're getting some relative position of the proof mass with respect to our frame. Okay, so I can then call this simply M times X double dot plus gamma times X dot plus kx is equal to f, simplifying our system to take into account everything. And this is the equation of motion for a simple harmonic oscillator, which is all an accelerometer is. Okay. So if we assume that x at t is equal to zero, so that there's no initial displacement, and we assume that x dot at zero is equal to zero, meaning that there's no initial velocity, we can use the Laplace transform to solve this differential equation. And what we will find is that our displacement x is simply our total force divided by s squared m plus s gamma plus k. Okay. Defining our resonant frequency as omega naught is equal to the square root of k over m and defining our quality factor as Q is equal to omega naught m divided by gamma. We can rewrite this equation for our displacement x as f over m divided by s squared plus s omega naught over q plus omega naught squared, and recognizing that force divided by mass is simply our acceleration. Our displacement is then acceleration divided by that same denominator, s squared plus s times omega naught over q plus omega naught squared. And our accelerometer then has a transfer function in the s domain that is simply 1 over s squared plus s omega naught over q plus omega naught squared. So effectively, that equation tells us how an input acceleration converts into an output displacement. That's all our transfer function is. Excuse me. So let's look at how this device behaves at low frequencies, defined as frequencies significantly less than omega naught, and at very high frequencies. Okay, so our low frequency response. All right, so for omega much less than omega naught. And we're going to consider S to be equal to J omega so that we have things expressed in the frequency domain as opposed to the Laplace domain. We will find that X, our displacement, is equal to our acceleration divided by negative omega squared plus J omega times omega naught over Q plus omega naught squared, okay? So this is just simple substitution of S is equal to J omega into our equation. Now let's look at things, okay? So if omega is much less than omega naught, then omega squared will be much smaller than omega naught squared. So effectively, this term right here is small in comparison to omega naught squared, so it largely goes away, right? Similarly, the product of omega and omega naught divided by Q should be much smaller than omega naught squared. So our imaginary part also goes away, and we find that this equation reduces to simply the acceleration divided by the resonant frequency squared, okay? So this relationship tells us that the displacement depends solely on the resonant frequency of the device, and it can be scaled down without affecting the performance by reducing the spring constant and mass proportionally. So effectively, since we know that omega naught is equal to the square root of K over M, our response only depends on omega naught. If we wanted to convert effectively a macroscopic accelerometer into the micro scale, if we change the spring constant and mass proportionately, it should still behave exactly as we expect, okay? So this is why accelerometers in the micro scale work. As long as we are operating at a frequency well below the resonant frequency of the device.
We haven't defined S.
Pardon?
We haven't defined S.
So S is the Laplace, like the Laplacian S. It is a frequency. So just hold on, let me think about how to do this. So S, the Laplace frequency, is equal to sigma plus J omega, right? So this is what the total value of S is, where this sigma, I'm trying to remember what it actually corresponds to, but it's the real part of the frequency, and J omega is, or omega is the imaginary part of the frequency. So like when we're working in the Laplace domain, everything is a function of S. That's all that I'm using here. So this S is just the Laplacian variable. I can't think of a better name to call it, right? Converting specifically over to the frequency domain where we're only dealing with the imaginary part of that Laplacian variable S, we have J omega, which is what's allowing us to look at how this device behaves as a function of frequency, where omega is the angular frequency, which is related to the linear frequency by a factor of omega is equal to 2 pi times f, the linear frequency.
So why we are dealing with the imaginary part only?
So effectively, we're looking at, you're kind of making an assumption here that we have sinusoidal excitation, right? So what I mean by that specifically, I'm going to have to explain this to you as an electrical engineer. So let me start there, okay? So if we have, this is an aside of things here, okay? So if we have a time domain signal, let's not call it X because that might be confusing because we're using that for displacement. Let's call it F as a function of time is equal to F naught, which is going to be the amplitude of our sinusoidal function, times the cosine of omega t plus some phase angle phi sub f. That is the real part of the exponential form complex number f naught e to the j omega t plus phi sub f. And at least in electrical circuits, working problems in the frequency domain as opposed to working problems in the time domain is significantly easier because it involves much less trigonometry and calculus and simply the direct application of algebra. We're effectively going to be doing the same thing here. So instead of finding a time-dependent transfer function for this thing, we found the frequency domain transfer function because the math was easier in the S domain. And then we're only using the imaginary part of S because we're saying we have a simple sinusoidal input signal that's causing this device to experience an acceleration, purely for the purposes of making the math less of a pain in the butt. And instead of, if we consider the input a simple sinusoid, we don't have to consider it to be the sum of a series of impulse responses, which will make the math annoying. So I don't know if that satisfies you, but that's the best explanation I can give you right now, looking at notes I wrote 12 years ago. So I'm happy to look into it further. I was hoping to get to revamping these, but I just didn't have the time to do it. So my apologies for that. But anyway, so S is the Laplace variable, and then we're looking at the imaginary part of the frequency, which corresponds to simple sinusoidal signals. My best guess would be yes. I might talk to Mikey about this and get a better idea of how the Laplace domain is used in the analysis of mechanical systems. My experience as an electrical engineer is all about how we apply it to circuits and all of that kind of good stuff, which is why I have to explain it that way. I'm happy to talk to some of our mechanical engineering faculty to figure out how the Laplace domain is used for mechanical systems. To me, just as a quick aside here, like I look at these systems not as mechanical systems or really electrical systems, but just as generic systems where the transfer function is simply what relates the input signal, whatever it happens to be. In this case, it's an acceleration to the output signal, which in this case is a simple displacement. And the Laplace operator, the Laplace, yeah. Is it an operator? No, curly L is really the operator. But working in the Laplace domain is how I learned to work with systems as a whole. And then it also, sorry, just to go on another tangent thing here, looking at S tells us whether or not our system is stable, right? So if we have a system where S is purely imaginary, we have a stable system. At least, at the very least, it's conditionally stable. If we have a system where the real part of our frequency S is positive, we have instability. And if the real part of S is negative, it is unconditionally stable. So we are looking at present conditional stability where S is purely imaginary. And we are doing that specifically so that we can see how the device behaves as a function of excitation frequency omega. Okay. A lot of words, hopefully some of them were helpful. All right, so if the device is operating at an excitation frequency omega that is much less than the resonant frequency omega naught, then we can see that the displacement is a simple function of acceleration, x dot dot, and resonant frequency, okay? Meaning that we can scale a design down from the macro scale to the micro scale simply by proportionally scaling spring constant and mass. However, we need to be careful because thermal noise vibrations increase as mass is reduced, which tends to increase the noise in the system. So sorry, that's the wrong color. Our RMS noise velocity, which we talked about in our last class, is given by KBT over M, right? So I'm simply pointing out that the smaller we make our mass, the larger RMS noise velocity our system is going to experience. Because as M gets smaller, X dot RMS goes up. Now let's look at high frequency response. All right, so traditionally, accelerometers that are operated well beyond their resonant frequency are used to obtain extremely sensitive measurements. So effectively, you would design an accelerometer with a very low resonant frequency, somewhere below 1 hertz, and then you would operate it at a higher frequency. So this is exactly how earthquake detection works. You have a really, really large mass system, which has a very, very low resonant frequency, and then any vibration that is experienced by it is typically well beyond the resonant frequency of the system, okay? So in this case, where omega is much, much greater than omega naught, looking at the exact same expression effectively. So this guy up here we are going to have what is effectively X is approximately equal to negative X dot dot over omega squared. Now, that being said, if we take the derivative in the frequency domain, what does that entail? Okay, so let's look at this expression right here to explain what's about to happen. Okay, if I take the derivative of this thing, what do I wind up doing? Multiplying by a factor of j omega, right? So if I have the second derivative of displacement with respect to time, I'm going to have a j omega times a j omega, right? So this is going to look like j omega x, excuse me, j omega squared x divided by omega squared. What's j squared? So actually, so this is one thing I need to make sure that you guys are on board with because I'm a hippie electrical engineer. J is the imaginary operator the square root of -1, because electrical engineers can't use I because that's current to us. Okay, so just as another quick aside here to make sure we're all speaking the same language, J is the square root of -1. Okay, so what's going to happen here effectively is that I'm going to have X is approximately equal to omega squared X over omega squared, or simply displacement is equal to displacement. What does that tell me? The proof mass isn't moving effectively at very high frequencies, which means we can't really operate MEMS devices in this regime because there's no way to restrain the movement of the proof mass. It's simply too small. Okay, so all of the accelerometers that we are going to be dealing with as a MEMS device will be operated under the natural resonant frequency omega naught. Okay. So that's what all of this went into. How do we translate a macroscopic accelerometer down to the micro scale? This tells us we need to be operating under the resonant frequency in order to get the behavior that we want. And we do that by scaling both the spring constant and the proof mass proportionally. So what do the dots mean?
No, I mean this J into
Mhm.
squared X. Is it supposed to have like dots?
No. Okay, so let's talk about that really quick. So these are all great questions. Okay, so X dot is dx by dt. X dot dot is therefore the second derivative of X. Okay, so if we look at this guy right here, because that's effectively what we're doing, we're taking the derivative of some exponential response thing with respect to time. So if we take the derivative of e to the j omega t with respect to time once, so let me put another orange line here to let people know we're going on a tangent, but that's okay. So if I have e to the j omega t, and I want to take the derivative of this expression, what I wind up getting is j omega e to the j omega t. If I do the second derivative, sorry, that should be a superscript. I'm going to get j omega squared e to the j omega t. Okay, so I am saying that the second derivative of X in the frequency domain is going to look like X multiplied by a factor of j omega quantity squared. So by me implicitly taking the derivative here, I'm getting rid of the dots and putting things in terms of the displacement. So the two dots on top mean I'm dealing with acceleration. I'm now linking the acceleration to the displacement using the derivative operation, and that's what got rid of them. Is that cleared up? Okay, great questions. Okay, so we have talked about the frequency response of the system, both in a low frequency regime where omega is significantly less than the resonant frequency, and the high frequency regime. Now we're going to shift gears to the time domain response. For those of you who suffered through circuits 2 with me, this is going to look real familiar, because essentially we're going to talk about the concepts of critical damping, over damping, and under damping. Yep, sorry for giving you guys PTSD, those of you that have suffered through multiple classes well, okay? So ideally, the accelerator output should follow the input acceleration instantaneously and without ever, meaning that any acceleration we see causes an instantaneous change in the displacement in the system, XM minus XF. But that isn't true for a practical system, right? It takes time for our system to respond to the input excitation, okay? So that's what we're going to look at here in the time domain response, okay? So in a MEMS device, damping is controlled, and what I mean by this is really caused by gas pressure inside the device, okay? We have seen that our damping coefficient gamma is inversely proportional to our quality factor Q. Okay. So now we're going to talk about some conditions, okay? So if Q, our quality factor, is exactly equal to 1/2, our device is considered critically damped. So what critical damping means is that we get the fastest possible response time without experiencing what I'm going to call overshoot. So I'm going to draw something here, and it's going to be a little bit out of context because we have not yet talked about over dampening and under damping, okay? So for a critically damped system, our response is going to look something like this. And this is going to be step response. So what we see to a unit impulse function. Actually, let me write that here. So if we put in as our input a unit step function, so it becomes 1 at t is equal to 0 and then stays 1 in perpetuity. What we are going to see as our response is something like this. It's a simple exponential response where x, our displacement, will be equal to our acceleration divided by our natural resonant frequency, omega naught. And then we multiply this by 1 minus exp of negative omega naught t. And then this is multiplied by omega naught t plus 1. Okay. And tau, which is not going to be strictly a time constant here, so let me define this. Time necessary to settle to final value will be equal to, in general, 2q over omega naught, which goes to 1 over omega naught when q is exactly equal to 1/2. Okay. So this is how long it takes for our system to go back to DC steady state conditions. Okay. Now, let's contrast that with, let me move this down some, an overdamped system. So if Q is less than 1/2, we have an overdamped system. So in an overdamped system, we have a slow response time without experiencing overshoot. So if I try to describe this graphically, looking at the step response again, where the blue curve is our input, a simple Heaviside step function. Our red curve is going to be our output. So we have a similar response. It just literally takes more time for us to settle. Okay. So in this case, our displacement will be acceleration divided by omega naught squared multiplied by, and this is going to be a thing here, 1 minus 1 over the absolute value of omega d, which I will define in a moment. Sorry, go away thing. Exp of negative omega naught t over 2q. And then all of this is being multiplied by the following expression, and I don't have enough room there, so I'm going to have to put it here. Omega naught over 2q times the hyperbolic sign of the absolute value of omega d t plus the absolute value of omega d times the hyperbolic cosine of the absolute value of omega d t. Close this guy off. Okay, so if I'm being entirely honest, I would like to look up what this equation truly means. Because this is rather different than what we see in an electrical system that's governed by a second order differential equation like this. So in an electrical system, all of the first part makes sense. Practically none of the hyperbolic sign stuff makes sense to me as an electrical engineer. So I want to look this up. Omega D is defined to be omega naught times 1 minus the quantity 1/2 Q squared. And I have in my notes here that this is going to be imaginary, which is where I believe all the hyperbolics are coming from. But that's just, I'm just doing a quick aside here because in an electrical system, effectively, we expect the underdamped system is the one that has an imaginary natural frequency. It's complex conjugate eigenvalues, which cause oscillation. And this system, at least what my notes tell me, which is why I'm a little bit confused by this, the presence of a imaginary frequency is leading to the exact opposite of oscillations. The oscillations are being suppressed. So that's where I'm having a little bit of disconnection. So I'd like to follow up on that for you guys and figure out what's going on. What is the condition for what?
Yeah, initial for this, like this first one, went down, right?
Right.
So, no, the second one went down. So what about the first one?
So the first one is critically damped, right? So I have it right here. So when Q is exactly equal to 0.5, the device is considered critically damped. Let me write that down here. Thank you for pointing that out. If Q is less than 0.5, we will consider the device over damped. Okay. And then the time it takes to settle, tau, will be approximately equal to 1 over omega naught over 2Q minus the absolute value for omega D. So 1/2. Yeah, I'll need to go back and look at this. I'm a little bit confused as to why those hyperbolics come out. The only thing that I can think of, so let me do another damn tangent. So in an electrical system, the overdamp response should look like A1 e to the negative yeah, negative S1T plus A2 e to the negative S2T, where S1, 2 is equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared. Okay. So effectively, what we would find for an overdamped electrical system is that our natural frequencies S1 and S2 are purely real. So we would consider this system to be critically damped when the quantity alpha is greater than the natural resonant frequency here. And it looks like a similar form. Like I think what's happening here is all of this math that's going on right here winds up getting buried inside those hyperbolic sine functions in order to expand it out in the form that it's being expected. But I just want to double check on that because it's making my head hurt to think about it. So anyway, let's circle back around and now talk about the underdamped response. So if Q is greater than 1/2 we consider our system underdamped. Okay, so underdamped means that we have a very quick response time with overshoot occurring. And so that means that my system response is going to experience oscillations. So graphically, for a unit step input, we are going to find that our output looks something like this. So it's going to come up to what it's going to settle to very quickly, but then it's going to overshoot it, come back around like so. And it looks like an exponentially decaying sinusoid there, okay? Our displacement X will once again be of the form acceleration divided by omega naught squared. Now we're going to have 1 minus 1 over omega d times the exponential of negative omega naught t over 2q. And then this is being multiplied by a whole thing over here. Omega naught over 2q sine omega dt plus omega d cosine omega dt. Close that parentheses and close that parentheses. So all of that is multiplied together. That to me looks fairly straightforward because that's roughly what it looks like in an electrical system as well, where omega d has the exact same definition. Omega naught multiplied by, where the heck is it? Square root of 1 minus 1 over okay, so I think I made a mistake in a moment, and this is helping me figure out a little something here. I'm putting this here. So let me write this more explicitly, because if I would have done this in my notes originally, this would have made more sense. 2q squared. And this should be this, let me go back here real quick. Yeah, so I want to make it more obvious that this is 1 over 2q and not 1/2 q. So now it makes more sense to me why this is imaginary. If Q is less than 1/2, 1/2Q is going to be greater than 1. 1 minus that quantity, we will have something negative under the square root sign, and it's looking like a negative, or yeah, a negative or imaginary frequency. That's okay. Sorry about that. So in this case, the quantity omega d will be purely real. And our time that it takes to settle will be simply 2Q over omega naught. All right, so before we talk about our last little thing here, which is going to be noise in an accelerometer, I want to ask you guys a question. If we were trying to design an accelerometer for a commercial application, let's say specifically designing an accelerometer to be used to deploy an airbag, which of the 3 response curves that we've talked about would we want? Right, but underdamped crosses a threshold faster due to a smaller input. We get overshoot, right? Meaning effectively that if we had designed an accelerometer to operate in an underdamped sense, noise could potentially cause the airbags to deploy. So in practice, we want it overdamped, but as close as possible to critically damped as we can get it. It's very hard for us to ever actually achieve perfect critical damping with a quality factor of exactly 0.5. So realistically, we're going to want something as close to 0.5 as possible, but overdamping gives us a little bit more wiggle room with respect to noise accidentally setting our device off. So we want it to respond quickly, but not so quickly to any arbitrary input that it immediately goes off. So just as a little thought experiment here about the practical implications of these different responses. Yeah, so why it goes off in a collision versus not going off when you hit a pothole. Because you are experiencing some change in acceleration when that happens. But it's enough to maybe cause it to jump, but not go beyond that threshold. If it were an underdamped system, it can go beyond that threshold so quickly, it might accidentally deploy. Okay. So our last topic here is mechanical noise in accelerometers. And so I am going to draw a simple diagram for an accelerometer. Okay. So in an accelerometer, based on the equation that we talked about earlier, an input acceleration, let's call this x dot dot, is converted into a force by the mass. So effectively, the gain of this stage of it is the mass. And then we're going to come back to this in a moment. That force is effectively converted into a displacement x by our spring. Where using Hooke's law, we're going to have F multiplied by a factor of 1/k gives us our displacement x. But we can't forget the effect of damping, where, as we talked about last class meeting, our mechanical damper is a noise force generator. So we will have Fn is equal to the root of 4 kBt times gamma. Okay. So we can see that our mass converts acceleration into a force that is then converted into a replacement. Our damping effectively adds some small amount of noise force to our system. So if we wanted to determine input referred noise acceleration spectral density, or effectively the threshold of the accelerations that we can measure, what would we do? We would refer the noise force from the mechanical dampers to the input. So our noise acceleration spectral density is going to be xn dot dot, I'm going to bar over it, is going to be equal to Fn divided by A. So we're referring it to the input. So that's going to look like 4 kBt gamma divided by our mass, or 4 kBt omega naught divided by mass times quality factor, all under the square root sign. Any acceleration that is experienced that is below xn double dot cannot be accurately measured. Okay. So what this equation implies, to some extent, is that our noise can be lowered by raising our quality factor. But this is not entirely true. So let me explain what I mean by that. We look at measured noise at the output, okay? So if we have some RMS noise displacement at the output, we can get the input referred noise displacement by simply taking XRMS, our measured noise at the output, and referring it by A1 times A2 because we have this two-stage amplifier here, which is going to be XRMS times mass divided by spring constant, or XRMS times omega naught squared. Where XRMS is kBt over m, we discussed that earlier. So we have the square root of omega naught squared times kBt over m. So the total input noise referred acceleration can only be reduced by increasing the size of the proof mass or decreasing the resonant frequency, which makes sense, right? The smaller our mass is, the more noise it should experience because thermal vibrations will have a larger impact. Let's see, talking about decreasing omega naught, right? So omega naught, let's go back to our equation here. Omega naught is square root of k over m, I believe. Yeah. So if we make our mass smaller, we inherently lower our resonant frequency as well. So this is a common sense kind of thing, right? If we want to have the smallest possible noise, we need to make sure that we're using effectively the largest mass that our design can handle so that it can't vibrate spuriously. All right, so that is accelerometers for today. Like I said, I'm gonna go back through and probably make some notes. We might do a quick revisited thing so that I can explain a little bit of the response stuff better at the beginning of class on Friday, and then we will move along to bigger and better things. I believe our next major topic will be looking at the different types of sensing mechanisms, and I think we're starting with electrostatic sensing. If I didn't say that in the syllabus, I'm changing it to electrostatic sensing because I know the most about that. So I feel more confident that I won't screw that up while I use the break to make out better notes on other things. So that is our goal. Thank you guys for your time and patience with me. I truly appreciate it. And I will see you on Friday.